I will give floor to my colleague in AFFINImeter, Juan Sabín, who is going to show you several applications that we to expand the potential of ITC based on AFFINImeter. Thank you.
Sí, sí. Este mejor. Se escucha mejor este. So good afternoon. So just tell me if the sound is not good. I will change the micro. Okay. Good. So my name is Juan Sabín. I also work for AFFINImeter. Before that, Eva Muñoz will show you how to work with AFFINImeter. So I want to tell you about some applications for Isothermal Titration Calorimetry that I think that AFFINImeter open new opportunities for new applications. So the main message that I want to show today is that you can do more things than you think with your ITC equipment, but you just need to have the right binding models, right? So yeah, I think it was clear from the talks that we have enjoyed this morning that there is many things that new applications that they can be done with AFFINImeter, but mostly of the limitations comes from the software, especially from the lack of available binding models that people can use to analyze complex data. This is the list of the binding models which are available right now in standard software. Using the notation, so there is two different approaches: independent binding and sequential binding, as Angela has already explained. With independent binding, you can analyze data for one set of independent sites or with two sets. There is a limitation in the number of sets. For instance, it's not possible to analyze polymers, for instance, with 4 different sets of independent sites. Sequential binding model for if you have a cooperativity. There is a specific model for competitive models. People use also this to make displacements, let's say. Which also has some limitations. For instance, these competitive experiments, they have to be done with one of the ligands always in the cell. So it's not possible to perform a competitive experiment with 2 ligands in the syringe, which in some cases this is very useful. And also the dimer dissociation model, which in some software we know that there is some problems and is not giving right results. So this is the more simplest binding model that you can imagine. So this is a one-to-one simple model. You have a macromolecule in the cell, you have a ligand in the syringe, there is a one-to-one binding model, and you create a complex. Even with this such a simple model, there are many, many equations behind. So I'm not going in detail, but you have to take into account the many different variables. So the concentration of the free species, the concentration of the complex, the heat releasing ejection, and so on. So just to show you that even for the simple model, there is many equations which have to take into account, right? So those are the kind of binding models that AFFINImeter can solve. So this could be quite complicated. So this is a real case. This is for instance, the model for a protein with 3 binding sites and 2 ligands competing to bind to these 3 binding sites. So all these reactions are possible. All these species are present in the cell, and they have to be taken into account in order to analyze correctly the isotherm. So there is 18 fitting parameters, and AFFINImeter can solve this with 8 different isotherms. So how can AFFINImeter do that? So I have summarized the main features of AFFINImeter only in 2. So one of them is that there is a limited amount of binding models. It can be designed by the user in a very easy interface. I think that Eva Muñoz will show later how I think that she will convince you that it's very easy to design new models. And the second one is that AFFINImeter can perform simultaneous global fitting of different isotopes. So you can perform with the same system different experiments in different conditions, and you can globally analyze. Even it's possible, as Angel explained before, to share parameters and make some limitations in the parameters. Those are the 2 main features, but also are important. This next two is that, of course, if you are studying complex systems and you have to perform different experiments, you need some tools to help you to design your setup experiment, so your experimental setup, right? So we provide what we call a simulation tool that will help you to make decisions about which concentration should you use for the macromolecule, which concentration you should use for in the syringe, number of injections, volume of injections, and so on. And also we provide a statistical tool to, let's say, to validate how good is your fitting, because this tool is especially good for analyze complex systems when you have many different fitting parameters. So you need something that you can validate statistically how your fitting algorithm is working. So we provide a tool to check, for instance, the local minima, which I will show you an example later. Well, and as I said before, I will focus today in some of the new applications that can be done now with AFFINImeter using Isothermal Titration Calorimetry. One of them is analytical discrimination in racemic mixture, global analysis in displacements assays, competitive binding with proteins with multiple binding sites, isolation studies, and aggregation and dissociation experiments. So the first one is analytical discrimination in racemic mixtures. I think this is a very interesting application from pharmaceutical industry especially. So this is a standard experiment where, again, so this is a very simple one where you have a ligand in the syringe, macromolecule in the cell, as you have a simple one-to-one model, and you can analyze this experiment, the isotherm, and you can get the binding constant, the enthalpy, and you also can get what is called sometimes the stoichiometry parameter, which in case that you are sure you have a one-to-one model, this parameter can be used as a correction in the concentrations. But this is like ideal case, but the truth is that in many cases, it's very common to have a mixture of different ligands in the syringe. So it's when people synthesize new ligands, it's very common to have, for instance, a mixture of different isomers. And then in this case, you don't have a one-to-one model. What you have is a competitive model where you have two different ligands who compete to bind the macromolecule. So if you have two different events, it's not a big deal if you are able to distinguish them, because if you have two different events, that your isotherm will have a two-step shape, and it will be easy to detect. The problem comes where, in one particular case, which is especially problematic, is when you have two isomers in the syringe that they interact with your target with very similar delta H. So in that particular case, your isotherm, it has a sigmoidal shape, which is very similar to a one-to-one model. So in this case, you can misinterpret your data and fit this to a one-to-one model, and in that case, it will give you the result for the lower affinity ligand. So what we suggest to do is, well, and I have to say this is a very common situation that you have a mixture of isomers in your syringe in heat-to-lead processes, in drug discovery programs, right? And the problem is that there is no available, in standard software, there is no available models to analyze competitive experiment when you have two different ligands in the syringe, right? So what we suggest is to perform a reverse experiment when you put the mixture of the isomers on the cell and the macromolecule in the syringe. And then in that case, if there is a set of ligands, it's more easy to see a two-step isotherm. So that's a good way to detect that you have two different ligands in the syringe, even if they have very similar delta H. So then you can also perform the direct experiment, and what we suggest is to use AFFINImeter to perform a global analysis of both of them, and then you can get, using a competitive model, and then you can get the parameters. So let me stress that if you just perform one experiment and you use the one-to-one model, probably you will fit the data and you will get the value for the lower affinity ligand. And this is a very important thing, because I really think that in in many pharmaceuticals industry, when they are working in drug discovery, they are ruling out some ligands which are good candidates just because they are misinterpreted the data, right? So I think this is applying the right model and performing reverse experiment with global fitting. I think it will improve the decisions in which ligands could be a good candidate for a new drug. Okay, but AFFINImeter is going forward, because more realistic situation is that, okay, you have a mixture of isomers on the syringe, you know the total concentration of the ligands, but you don't know the concentration of each one of them. And this is a really problem, right? So AFFINImeter can solve even this problem, right? So what we have developed is, before I say that there is in standard software there is one stoichiometry parameter to make the correction in the concentration, but in AFFINImeter you have 3 different corrections in the concentration, one for the macromolecule and 2 for the 2 other ligands, which are usually in the syringe or in the cell. And we can fit this independently in order to get information about the concentration that you have in the syringe, right? So let me show you one example. This is a real case. We were working in a project with a pharmaceutical industry. They knew that they have a mixture of isomers of a candidate for a drug, but they didn't know how much they have of each one of them. So we performed an experiment where we put the mixture of the isomers on the syringe, the target on the cell. In this case, these isomers they have different enthalpies, so that's why we see a 2-step isotherms, and we analyze this using competitive model, but we include the corrections in the concentration as a fitting parameters. So that means that we were able to give them the information, the thermodynamic information for both ligands, from the enthalpy and the binding constant, but we were also able to tell them, so you have 55% of the isomers bind with high affinity and 45% bind with weak affinity. And this was information that it's only possible to get with using Isothermal Titration Calorimetry combined with AFFINImeter. And I think it was a very useful information for this company. The second application I would like to talk about today is global analysis in ITC displacement assay. So first of all, I will show you, this is the standard procedure that mostly people use. If you want to know with high precision the binding constant of a system, or this displacement assay also is used when you have a ligand with very high affinity out of the range of ITC. So people usually measure this. They have a very good measure of the enthalpy, but it's not possible to get with precision the KD. So what they look is, they look for another weak competitor. They perform the experiment, they get the thermodynamic information, and they perform a competitive experiment with the weak competitor in the cell and the high affinity ligand in the syringe. And they can extract the information of the high affinity, take into account the information from this. The problem with this is, first of all, there is a limitation. In order to perform a displacement assay, you have to have one of them on the cell. And sometimes to have both competitors in the syringe, it's much more interesting. You have more, you get more information from this. And the other problem is that you are losing some information. Somehow you have a very good measure of the delta H that in your analysis you are losing, right? So what we suggest to do is, first of all, using AFFINImeter you can perform an extra experiment, which are put the high and the weak competitors on the syringe. And as you see, for instance, in this example, this has more features, so it's you can get more information or better information, let's say, with this experiment. And then you can perform a global analysis taking into account 4 of them. And that will give you more reliable data of your binding constant and entropy, even for the high affinity ligands. The third application is the study of competitive binding with protein with multiple binding sites. So this is the example that I gave you in the very beginning. So this is a real case, a protein with 3 binding sites, 2 ligands, and this is the model that you have to apply in order to analyze this system, where here we take into account all possible species, even if the protein is full covered by one of the ligands or the other, or all intermediate species you have to take into account into analysis, right? So you have 16 fitting parameters and 8 reactions. So if you have such a problem, so a way to go is, well, you need more data, right? You try to analyze one single isotherm and you try to fit 16 parameters. For sure you will get a fitting, but probably there is no meaning in this value, right? Because whatever thing will fit. So you need to perform more experiments and then make a global analysis of all of them. So first of all, you can take one of the ligands and make a titration to the target. and you will get one isotherm. Take the other ligand, and then you use AFFINImeter to define a binding model, which is a simple 1 to 3 model. This is a simple one. Then you take the other ligand, you perform the experiment, and you also define a new model, which has also is essentially the same as the one is in before. And then you perform a competitive experiment, and you design this model. This is a competitive model for a protein with 3 binding sites. And you can get all these isotherms and analyze them globally. But you need to make some restrictions in your analysis because you have many, many parameters, but some of them are the same. So you can share parameters. So you can say, for instance, that the parameters constants, the thermodynamic parameters of the first model has to be the same as those ones. And you can say using AFFINImeter that the thermodynamic parameters of the reaction has to be the same as those ones. And then you are decreasing the degree of freedom of your fitting parameters. And then you can get this nice fitting, this is the red line, are a global analysis, global fitting of the 3 isotopes. Of course, you still can think that maybe you trust or not your fitting procedure. So that's why we provide this statistical tool to analyze the local minima of the fitting. So what AFFINImeter really does, it gives you the result for the best fitting, but we provide the results for 10 different results from 10 different initial seeds. And those seeds are, as Angel said before, are randomly chosen. So we provide not only the best solution, but all the possible solutions, and checking, I mean, if 10 different initial points gives you the same results, that is a good reason to trust your fitting. So if you get different solutions from different initial points, then you can start to think that maybe you have to change your seeds or change the range of each parameters and so on. And also because some mathematical solutions has no physical minimum. So you also can check for local minima in order to be sure that your analysis is good. I will not go in the next one. This is one example of this 3D and 2D projections of all these 3,000 interactions for a pair of fitting parameters, but I think Angel already showed this. The fourth application that I would like to talk today is this mesialization studies. So this is, I think, Daniel already showed something very similar, that this is a typical isothermal for mesialization where you have, usually you have micelles on the syringe and you titrate it and you get this isotherm. So mostly people, what it does is make a qualitative analysis of this. You can get the delta H of the mesialization and the CMC just by extrapolating this curve and take the middle point. But there is no theoretical background in this analysis. So we provide a specific model to measure mesialization where the fitting parameters are the dilution heat of the monomers, the dilution heat of the micelles, the delta H of the mesialization, and also the aggregation number, the mesialization number, which is a parameter which usually is very difficult to get. It can be done with ITC, right? So we check this with 2 different surfactants to validate our model at different temperatures. This is the other example, and we compare the aggregation, the mesialization number, the aggregation number, compare the values with the fluorescence, and they agree very well. So meaning that we can think that we validate somehow this model for micelles. But additionally, we not only get the mesialization number, we get all this extra information using ITC, and I think that it's very useful and very complete model. And the last application is aggregation and dissociation studies. So actually, this mesialization model is a particularly case of a more general model where used for aggregation, general aggregation, dissociation. Actually, we use this mesialization model to study the dimerization of a protein. So we get this isotherm. We use exactly the same model as we did before, and we get aggregation number of 2.09, which is fairly well if we know that there is dimers on the syringe, right? But AFFINImeter is very flexible designing models, so you can create dimerization, very simple one, but you also can go there is no limitation in the number of aggregates. So you can create a model where you have dimmers and there are trimmers. Or you can combine aggregation with binding models. For instance, there are some ligands who works as a linker. They first bind to a macromolecule, and they work as a linker to other macromolecules. So this is a dimerization induced by binding, right? Or it could be the other way around. It could be binding induced by dimerization. So some ligands, they need to be dimmers before they bind. So you can write all these models very easily in AFFINImeter. So this is the scientific thing that I think that also Angel showed before. And I just want to finish with the first sentence that I was telling you before. So I really think that there is more things that people can do using ITC, but you need the right binding models. I know that mostly people are using ITC to just calculate KD with a simple one-to-one model, but I really think that if we develop more software, more binding more models for the ITC, even there is more chances to increase more users, to increase the market for food, industry, cosmetic research. I think that will be very interesting in this visualization models or aggregation and so on. So that's all. I will be very happy to get some questions.
Just a note to my own data, Juan. The titration curve which you showed from my present publication, it's not injection of the dotacyl sulfate, which is above the CMC. It's below CMC.
You mean in the data?
Yeah,
I did wrong. Yeah. So
just to be correct, it's yes, this plot. It's injection of dotacyl sulfate from the syringe, which is below the CMC.
You mean with monomers in the syringe below?
Yeah.
Okay.
Yeah, so yes, it's below. It's just, this is the aggregation. This is the formation of mixed micelles of dotacyl sulfate in the solution of the ionic liquid, which the ionic liquid is at 100 millimole or something like this.
Okay, so what's below is CMC.
Below
okay.
the CMC
yeah,
of the surfactant in the syringe.
Yeah, okay.
Just to be correct.
Thanks for correction.
You showed early on an analysis for, I think, a macromolecule dimerizing, binding different ligands in different sites. And you had, I don't know whether it was 18 equilibrium constants, but then you mentioned something about 8 parameters. Does that mean that AFFINImeter knows about the principle of detailed balance?
Which example do you mean? When I showed this this one?
No, here it doesn't seem to play. Can you go? It was really far in the beginning.
Okay. So that one?
Yes. So in this case, you have in the first circle, well, square, you have a K1, a K7, K2.
Right.
And
yeah.
K
This is those equations. Those relations are not needed.
Okay. So that is.
Yeah, it's less reactions.
Okay, that was basically my question.
Okay.
Is that something that AFFINImeter recognizes itself, or is it something that you have to tell it?
It's something that will recognize, because when I think maybe I will show in the next talk. So it will not allow you to put 2 reactions with the same result. So it will know that somehow.
Okay, thank you.
Okay, so if there is no more questions, I think that we have a break now.
Is stoichiometry a refined parameter?
Yes, I mean it is actually. Yeah, I mentioned that there is 3 different parameters for the correction of the concentration of the macromolecule into ligands, but one of the parameters can, of course, as stoichiometry. Yeah. So maybe we can make a break now and come back later for Eva Muñoz talk. Thank you.